Hello. OK, is it working? Can you hear me? Perfect. All right, so let's talk about debugging. So I don't know about you, but I have pretty mixed feelings about debugging. So sometimes it can be a lot of fun. Maybe you're stuck on some kind of problem, you don't really know what to do. So you go for a bathroom break, and sort of as you're sitting there, you're thinking about it. It's like, oh, maybe that's the problem. So you rush over back to your computer, you type something in, and oh my God, you just solved it. And that's the best feeling ever, right? But there are also things that make debugging not so much fun. So maybe someone told you, hey, by the way, there's a bug. This is what I did. And you do that, and you don't have the bug, right? Or maybe you can sort of reproduce the bug locally, but as you then try to inspect it with a debugger, or maybe you add some print statements, the bug suddenly goes away. Or maybe you have to go through a long sequence of steps to get to the point where the bug even happens, which can be particularly fun if you're in a step debugger, and then you accidentally step too far, right? We've all done that. And then you go through all of those steps again. Or maybe you're like, step debugging isn't really for me. I'll just use print instead. But that doesn't really solve the problem because, well, now you need to add another print to get more information. And then you go through all of those steps again, and the Heisenbergs and all of that. So if I could wave a magic wand and sort of make all of those problems go away, I would do that immediately. Now, it just so happens that I've been working on a magic wand for the past 2 years. And by the magic wand, I mean I worked on a record and replay debugger. So let me quickly define that term. In a traditional debugger, what we do is we have a live process. Sorry, there wasn't enough space on the task. So we sort of have a live process that we attach to, and then we can sort of pause it, look at the state, set some breakpoints, do some stepping, resume it. The problem is just like, if we've gone too far, well, we have to start at the beginning again. Now, contrast that with the record and replay debugger. What we do here is we record the execution once. So we still start the process, we attach to it, we inject some instrumentation in order to record everything it does, and then we can replay it as many times as we want. And going back to the things I like so much about debugging, we can see that the first 3 problems, they basically just disappear. Right? If it doesn't work on your machine with the bug, just let the other person who created a recording send that to you. Now you can reproduce it. Heisenbugs, well, as long as you can capture it once, you can replay it as many times as you want, with as much instrumentation as you want. If you have lengthy reproduction, well, that's a part of the recording, right? And as for stepping too far, the thing that we used to do manually, where we just sort of go back to the beginning, go step by step again, until basically just before where we were before, well, the debugger can now do that automatically. And as for like the print debugging problem, we'll see something we can do about that later. For now, I want to no, that's the last slide. That's at the end. For now, I would just want to show you what this debugger can do. So I've prepared a little Lua script here. It's just like a Fibonacci function that we call in a loop in the function in the something function. We generate some random values, and then we print those values. Now, we are going to run this program with a local build of Lua I have, so like the build debug Lua. And the problem is just that, oh, worked first try. Sometimes this seems to crash, even though it's a perfectly valid Lua program. That's because I introduced a bug into the Lua binary. And our goal for today is going to be to figure out what that bug is. So the first thing that we'll do is we'll just try some print debugging. Oh no, this is not looking good. This is supposed to be a diff view, but well, this works too, like a side-by-side thing. OK, so we just add some prints so we can look at the values. Maybe there's some kind of pattern that we can spot. So let's see if that works. OK, we can run it a few times. Well, I guess the bug seems to have disappeared. So what we'll do instead is that we will run the program, but we will create a recording of it with my debugger, because we seem to have a Heisenbug here. So we'll do CLI record 2, because this is version 2 of the recorder. And let's run it a few times. Oh, that is a bug, but that's a bug in my system. OK, and there we go. Now we captured a recording where the bug in Lua happens and not my bug. So what we can do now is we can use the debug program to take the last one of these. Let's see which one that is. That one should be it. Oh, no. Oh no. That should also not have happened. And it hasn't happened so far. Let me just do all of that again. So we'll create a new recording of the Lua program. If this doesn't work, we're in trouble, by the way. So everyone pray. OK, that's looking better. So just to make sure we've actually captured the bug here and we can reproduce it, we can use the continue command like in any other debugger. And we can now see we continued, and there is the bug again, right? But if we were in a normal debugger, we would have already gone too far, right? The bug has already happened. So what we can do now is we can use the undo command. Wow, we're back at the beginning. Isn't that cool? And I just want to show you some other basic debugger functionality that we have now, that I have, I guess. So we got breakpoints, stepping, expression evaluation, stuff like that. So we'll put a breakpoint on main, and we'll go there, and we can see we are now in the code in the Lua VM, or in the Lua CLI, that sort of sets up a new Lua state. We can skip over that, do some other stuff, as you do. And oh, whoops, we went across the bug again, but no problem. We can just undo. So it seems the problem is somewhere in this P call there. We could now step into that, but that's not really how you want to debug this sort of thing, right? We want to sort of get closer to where the bug actually is. So what we'll do is we'll put a breakpoint on Lua v execute. We'll go there. I'll step forwards a few things until I get to the comment that I want to show you guys. Main loop, where is it? Main loop of interpreter. So this is in the Lua virtual machine. This is the loop that goes through the bytecode of the Lua code that we're executing. It reads one instruction at a time. It let's do that. Right, we VM fetch, that reads one instruction. And then it has a dispatch on the opcode of the instruction. And this is basically just a giant switch. So we check, is it an add? We do an addition, and so on. So what we can do here is, well, we can look at the local variables. We can see, OK, I is the instruction, seems to be 0x51, whatever that means. We can see the PC right there, the Lua PC. OK, there seems to be some code. And what's sort of partially on the screen here is the base pointer, which points to the stack frame of the current Lua function. And there seems to be some kind of value there. But wouldn't it be nice if we had something a bit more readable than just some numbers? So what we can do is I've prepared a little sort of a plugin for the debugger. We can kind of think about it that way, that we can add using this preload add Lua stuff command. Right? And now what we can do is we can use the print command to have a look at one of those values. So if we just do print I, the instruction, we get 0x51. If we do Lua opcode I, then we can see, oh, OK, it seems to be a var prep instruction. So that's pretty cool. And we can also have a look at one of those stack values. So we can go p Lua to string base sub I.val, not I, it's just 0. We seem to have like a 0 value there. The next one is a print string, and then we have a nil value. OK, so we've got some basic debugger functionality. We can do single stepping, we can look at the state, we can use some sort of plugins to look at the state in a more structured way. But we kind of want to debug this issue, right? So the next thing we're going to look at is how we can use print debugging in a time travel debugger. That might seem a bit weird, but you'll see this is a really good idea. Trust me. So the way that's going to work is that we have a script file where we'll basically just automate the process of what we just did. We'll put a breakpoint in the Lua function. That line there is the thing where the switch statement is. And whenever we hit that, we'll be called by the debugger, and we can print the Lua opcode. So let's see what happens when we do that. We can use the scan command with the prints.0.js, and we can see, perfect. We can now see all of the instructions that the Lua program executed without even having to had to modify the program, right? So we have the same recording as before, and that's pretty cool. So now before we continue with debugging the program, the problem here, I want to indent these instructions a little bit based on the call stack depth so that we can sort of get a better idea of what the structure of what's going on here is. And the way we're going to do that is that we will introduce a depth variable into our script, an indent function, and then we'll just indent the code. But of course, we still need to know what the actual call stack depth is. So what we do is we add 2 more breakpoints, because Lua is nice enough to call these 2 functions at the start and end of a Lua function. Now, if we do that, by the way, I also implemented this history thing yesterday. So before I would have had to retype the entire command from scratch. So that didn't work. Right, this was the first one. The second one is that. And that is also looking quite interesting. The reason that's looking quite interesting is because we have a bit of a problem here where the return, there seems to be a return, but there's no unindent. And the reason for that is there are some optimizations in Lua where if a function just returns 1 or 0 values, then this function here that we're relying on with the pause call isn't called. Doesn't really matter. We just add some more breakpoints, and then we're all good. So let's have a look at that. Perfect. So now we can see, well, there are some function calls. There is this op LTI, less than immediate, and some other stuff. And now we want to really get serious about debugging this issue, right? So we figured out this is what's happening, but we don't really know what the state of the program is yet. We would like to know, well, what are the values on the stack? So what we'll do is, just like before, we're going to, hang on. We're going to use expression evaluation with this Lua to string helper function, and we'll just, whenever there's an instruction we execute, we'll just go through the stack and print all of the values. So let's see what that looks like. OK, perfect. So now we can see, well, what's going on. And if we look at those integer numbers over there, we can see that does look like a Fibonacci function. So we have like 4, and then -1, that's 3, and so on. But what's kind of odd is that at the end here, we can see that suddenly there's a less than immediate instruction, and everything is just nil. That seems a bit odd, because up here there is a 2, and up there there's a 1. So it seems that we might have found where the bug is, right? And just to verify that, I can quickly do the continue thing, where we see the bug thing again, the error report, and we can see we tried to compare nil with a number. And we have nil there, so that is probably the bug. But the thing is, like, now with normal print debugging, we would have to go back, add some more prints, and then, I don't know, we'll see what happens. Or maybe we have to figure out how to get a debugger into this state. But that also doesn't really help us, because once we're there, well, we already know the value is nil. So what do we do? Well, this is where we use the power of time travel. So we're going to add one more thing to our print debugging session. We're just going to use this little variable tick right there, and we'll print that with every instruction. The tick is sort of like a logical timestamp that represents where we are in the replay. We can see that, OK, there's some numbers there. And it's going to get really cool now, OK? Prepare yourselves, right? We're going to copy this value, which is the logical timestamp. We're going to use seek to go to it. And now we are at the dispatch thing, which is where we put the breakpoint. So let's just go forward one step. And there we go. We are exactly where the bug is actually happening. Is that worth an applause? I think so. OK, but I actually baited you, because now it's going to get even better. So let's step into that. And we can see, OK, well, we are in some kind of helper function that takes these values here. And we can look at those again. We can go like print Lua to string on the P1 thing. And we can see, OK, yeah, we indeed have a nil. And if we go PV2, we can see we're trying to compare nil to 2. But now we have this problem again. Well, where did this nil come from? And usually this is the point where you go take your bathroom break and you try to figure out, do you have some kind of idea, like how could this have happened? How could possibly a nil have come here? But in this case, we can just ask the debugger. So we can use the GD command. GD is sort of inspired by the NeoVim shortcut go-to-definition for LSP stuff. And we can say, please, debugger, tell me where this expression came from. And we'll go p1.val, is it val? Oh, no, I don't remember. .tt_. OK, that is not the thing. it was just GT underscore. So we'll basically ask, where did the type tag of this Lua value come from? And when we do that, the debugger has just gone backwards in time. So we can see that the tick value here it was 3500 before, and now it is 23 something something. So we actually went backwards in time to the point where this nil value was created. Now the question is, was that actually okay? Should the program have done that or not? And to get a better idea of that, well, let's see what the value was before it was overwritten by a nil. So we can go print Lua to string on the new stack at position I. Here we have to do .val. And we can see before it was a number 0. And, well, let's just figure out where that one came from. So we'll do the thing again where we ask gdexpr, where did this thing come from? And we can see there's actually a lot that happened just now. The debugger went through multiple steps. There was a mem copy, another mem copy, and then we were somewhere in the interpreter. And now, well, it turns out we were in this op add immediate instruction that created this value 0. And what's really cool is that we can now look at the timestamp here. And we can see it's something like 0103. And if we, oh, that is not a lot of space. Let's see if we can find it. So back here, if we look at the timestamp of this thing, there is like 0050 and then 011 something. So it seems to be, oh, there it is, between these two, and it's actually this add instruction that created this value, and then we had a call, and then it somehow became nil. So it seems to be the case that this, the thing where we overwrote the value with nil was not supposed to happen. So we have found the bug. Now we just have to fix it. By the way, of course, we can just undo to go back to where that happened. So it doesn't really matter like what the actual bug is here, but the point is just, if you reason about what the for loop is doing, you can see that minus should be a plus. And that's the only thing I changed. And we just managed to find one of those single character bugs that usually would cost you a lot of time because you have no idea how the nil got here. And we managed to fix that, well, in 15 minutes with like a bunch of detour where we did some print debugging. But really the thing that helped us here was this gdexpr command that allowed us to go backwards from the value that looked fishy to the code that actually created it. And that is the power of time travel. Thank you. OK, questions?
All right. Hello, test, test, levels, levels. I have the mic here. Felix.
What are your UI plans for this?
Oh, yeah, big plans. Well, could you clarify that question, like what my UI plans are?
Are you planning on a graphical UI, something that reveals more ambient information, the way
Right.
we
Yes.
know from like RAD debugger and things like that?
Yes, the plan is to have a very sort of graphical interface. Actually, I can show you something I want to do. Let's just show a bunch of private files. Let's go into BSP demos. OK, so this is something I worked on for a jam a while ago. And it's something it's basically like a hex dump of some values in memory. But we can see that I use the debug info that I get from the debug info, from the whatever, to figure out, well, OK, here is like the main function. There are some local variables in it, and that's the type. And so that's really cool on its own. We can sort of see the contents of memory with their types. This works by sort of starting at the global variables and then tracing pointers to find everything. And obviously something that we could do in this case is if we find some weird value here, we could just sort of click on it and ask the debugger where that came from. So that sort of maybe gives you some kind of idea of what I want the UI sort of to be like. It's like clicking stuff.
This looks amazing. Great job. I'm just wondering about the overheads. Like,
Yes.
what's it costing to run? Are you going to be able to run this on a 3D game that's pushing hundreds of megs through RAM every frame? Or
Yeah, I mean, you can run it. The question is just like, how much is the overhead, right? So currently we're talking somewhere between 5 and 10x, but I think I can get it closer down to like maybe 2 to 3x. But that's just sort of speculation.
Next question.
Thank you.
What architectures are you supporting right now?
Right now, it is just macOS and ARM. I'm planning to do other platforms in the future, but I've been on this for like two and something years, so it's going to take a little while.
All right, one last question.
I've never used a time travel debugger at a job I've been working, but I've seen a lot of people demo something like that on the internet for like various projects. So like it sucks that it's not more mainstream, and it's cool you're doing that. But I'm wondering, what did you, when implementing this, what did you take from what's been done before, and what did you do differently?
Okay, lots of things. So initially, I sort of just thought about it myself, like how would this work for native code? This is WASM, by the way. I started in WASM. And then eventually, after I figured out how to do it, I discovered the RR paper, and I was like, oh, yeah, I do that as well and that as well. But at some point, I found out about WinDBG, which is a version of this for Windows. And it uses quite an interesting approach where they sort of treat memory as non-deterministic, which allows them to run threads in parallel. And you can run through across system calls that you don't understand. And that is a technique that I borrowed from them. I improved it a little bit, made it a little bit faster, because their thing has like somewhere to 50 to 100x overhead. So 5 to 10x is already a little bit better.
All right. Thank you very much. Let's give a round of applause.
Thank you.